Welcome to MOVI-C Cabinet and Decentralized VFDs 201. This is session 16, Custom Drivetrains. A big congratulations is in order. You've reached the final session of the class. Good job for coming this far. This is a relatively short session, so without further ado, let's dive right into it and wrap things up. In this session, we're going to learn a bit more about drivetrains. We've been working with them in other sessions, and we talked about them in some detail when we talked about positioning. We now need to dig a little deeper. Just by way of review, remember the drivetrain is everything that helps produce the motion. That includes at least a motor, but it could include a brake, a gearbox, transmission elements, an encoder, possibly an external encoder, of course the control mode that the VFD uses to control the motor, and possibly a custom unit if we don't wish to use the default units. Setting up a drivetrain is relatively easy. What you should always do first is configure the motor, the encoder, and the control mode just to get the basics in place, and then from there you can add further components. The way you do this is you click the drivetrain setup button, which will reveal a number of additional components that you can add, like gear units, transmission elements, encoders, and user units. A few important notes here. Gearboxes and gear trains scale rotary motion up or down, but it stays rotary motion. In other words, its basic default unit will be the rev. However, if you incorporate belts, drive wheels, or spindles, these translate rotary motion into linear motion, which causes an automatic unit change from the rev to a linear unit, the millimeter. Since we are a European company, we use the metric system. All components that you add to a drivetrain must be specified in metric units, usually millimeters. If you need to use an imperial component, you're going to have to convert its units to metric in order to enter them. Now, as far as the actual positioning unit at the end of the drivetrain, that is fully customizable. You can change this if you wish to either a standard unit from a different system, like inches, for example, if you're using imperial, or even a custom industry-specific unit, like pallets or boxes or even cows. It's up to you. In this session, we're going to look at how you do this. Let's start by talking about adding a gearbox to the drivetrain. This is fairly common if you have a gear motor. Now, if you're using an SCW Eurodrive gearbox, then things are pretty easy because you have a complete list of all our gearboxes with all the ratios they support, and you can just pick it directly. But if you're using somebody else's gearbox, then you can add the third-party gear unit. You can either enter the ratio as a decimal number, or if you wish, you can enter the gear ratio by entering the number of teeth on the individual stages. By default, there's just one stage, but if you need additional stages, just click the plus button and you can add more of them. If you add a gear train, you enter it much the same way, either directly as a decimal fraction to indicate the ratio, or you can enter the teeth information in a standard fraction format. If you're using a toothed belt for a transmission, then you need to enter two pieces of information. You need to enter the number of teeth on the drive wheel and the pitch. And this pitch is metric pitch, which is the distance in millimeters from tooth to tooth. If you're using a drive wheel, you may enter the information either as a wheel diameter in millimeters or the wheel circumference in millimeters. Again, it's up to you. Whichever one you don't enter will be calculated from the one you do enter. If you're incorporating a drive spindle, all you have to do is supply the metric thread pitch. This is not the way we do it in the United States typically, where we have threads per inch. This is the European style, where you enter the thread pitch as the distance tooth to tooth in millimeters. And finally, if you want to have a user positioning unit, you incorporate it at the very end of the drivetrain. Now you can define standard units, such as inches or feet, or you can create application-specific units. All you have to do is specify a conversion factor. But there is one important rule. You may not enter the conversion factor as a decimal fraction. It must be entered as a conventional standard fraction. In other words, one with a numerator and denominator. That's very important. Let's see how we set up a custom unit. The first thing you do is you add the user unit to the end of the drivetrain. It looks like a bunch of bottles. And then you go down here and you switch to user-defined unit. You then enter a label for the unit. It doesn't matter what it is. MOVI-Suite has no idea what you're typing in. It's just treating it purely as a label. And then finally, you enter the conversion factor as a standard fraction. In this case, we're going from millimeters to inches, so we use the standard fraction 10 over 254, and that is because there are 25.4 millimeters per inch. Remember, we're not allowed to enter decimal fractions, and so we enter it in this form. However, notice that MOVI-Suite does calculate it as a decimal fraction for you, just to help you confirm that it's correct. Now, once you've done that, you can set the precision of the different positioning units. You can set the distance. It defaults to 2 decimal places, but you can change that. And then you set up the speed and acceleration units and their decimal places. By the way, it is a very good idea with all MOVI kits to use consistent units for everything. So in other words, don't use inches for distance and RPM for speed. You should use inches, inches per second squared. One thing that's very nice about MOVI-Suite, it shows you how each component affects the motor's original rotary motion. For example, we have a fairly complex drivetrain here. We start right here at the output of the motor. We have one rotation of the motor, and MOVI-Suite tells us that when it goes through the gearbox, it becomes 1/4 of a rotation because we have a gear ratio of 4:1. The toothed belt translates that into 250 millimeters of linear motion, and the custom unit translates that to 9.84 inches of linear motion. So if that motor turns 1 revolution, you're going to get 9.84 inches of linear motion. Also notice this, you can enter a ratio for the encoder as well, which is normally attached to the back of the motor. In most cases, it will be 1:1 if it's attached directly, but if you have a geared encoder, you can enter that gear ratio and that too will be automatically incorporated. MOVI-Suite and the MOVI-C VFDs working together are very intelligent, and they take a lot of the heavy lifting off you. I think it's time for our final lab. So please take out your lab manual, turn to the last lab, pause the video, and do the lab. All right, we're going to do the lab walkthrough now, so if you weren't able to do the lab, watch me do it right now. This is an exciting moment. We're doing our final lab. We're going to create a customized drivetrain, and with that, we're going to wrap up our course. Let's go ahead and get our drivetrain customized. First of all, we need to save our lab as Lab 9. And we're going to reconfigure our drivetrain. I'll double-click my axis circle. And I'm going to go to Drivetrain DT1. And what we're going to do is add a few things onto it. First of all, let's add a gearbox. So I'll click Drivetrain Setup, and I'll pick Gear Unit, click plus. That will add it on. Now I'm going to click the gear unit, and I'm going to say Select from Catalog. Of course, we're going to use an SEW Eurodrive gearbox. We'll use an R gearbox, so I'll pick the R series. And I'm going to pick an R27 and add that. And I need to pick a ratio, and I'm going to use the 4:1 R27. So it's going to divide our motor speed by 4. Next, we need to add a drive wheel. So again, I click Drivetrain Setup, and I pick Drive Wheel, and I click plus, and then I click the wheel, and I need to enter either the diameter or the circumference. I'm going to enter the diameter, and my instructions tell me to use 84 millimeters. Notice the circumference gets calculated automatically. So that's our drive wheel. And now finally, we're going to add a user unit. We're going to convert to inches. Move away from metric here for a few minutes. So I click Drivetrain Setup again. I pick User Unit. I click plus here to add it on. Going to select it here. And first thing I need to do is change it to user-defined unit, and I give it a name, and it doesn't matter because the name doesn't actually mean anything. It's just a label, so I'll just type in inch. But what does matter is the conversion factor. I need to show the relationship between millimeters and inches. Well, I know there are 25.4 millimeters per inch, so 1 over 25.4 would be an appropriate conversion unit. But remember, we're not allowed to use decimal fractions in MOVI-Suite, so I'll instead type in 10 over 254, which is mathematically identical. So there we go, that's our conversion factor. Notice MOVI-Suite thoughtfully converts that to a decimal just for your edification, and I look at that and say, yep, that looks like the right conversion factor. All right, finally we can select our precision here. Now I'm going to leave my number of decimal places for positioning to 2, so we'll keep 2 pseudo-decimal places, but I am going to change my speed unit to inches per second, and I'm going to change my acceleration unit to inches per second squared. It's a really smart idea in MOVIKITs to have consistent units across distance, speed, and acceleration. I'm going to leave the number of decimals to 0 on both of these because I do not need more precise speeds or accelerations. That completes configuring our drivetrain, but we have to do a couple more things to wrap this up. Notice that this button has appeared up here, Activate Scaling, and the drivetrain is sort of grayed out. That means the changes I've made haven't been fully activated, so I need to do that. I'll click it. Notice now it ungrays itself and it tells us 1 revolution of the motor passing through a 4-to-1 gearbox, turning a drive wheel with a diameter of 84 millimeters, going through a conversion produces 2.6 inches of linear motion. That is going to be very useful to us down the road. We want to remember this number here. All right, now I need to apply this to the drivetrain, so I click Next and finally Transfer Data to Device. And I click Transfer Drivetrain and yes, activate Startup State. And there we go. Everything is all set. We've now reconfigured our drivetrain. We need to test it out now. Remember this, I don't actually have a gearbox or a drive wheel attached to my motor. I just have my plain old boring flywheel. So what we need to do to test it is we need to figure out how many turns the motor is going to turn for a specific position value. Now, we know that 1 revolution of the motor produces 2.6 inches of linear motion. If I said I want to move my application 22.1 inches, how many rotations will the motor turn to make that happen? Well, if it's 2.6 inches per revolution, then what I can do is take that 22.1 inches that I want to move, divide by 2.6. The answer is about 8.5. So the motor should turn 8.5 revolutions. What we're going to do is run the motor really slowly so we can count those as we go along. All right, so let's test things out. We're going to go into MOVIKIT Diagnose because remember our positioning MOVIKIT is still there ready to run. I'll take control of my axis here and I'm going to remove controller inhibit and enable my drive. Now I need to reference my drive, so we better do that first. Remember, we are still in limit switch referencing mode. I'm going to pick reference travel with the offset by field bus. I'll make sure this value is set to 0. I will turn on bit 7. My drive will start heading towards the clockwise limit switch. I'm going to turn DI02 off to simulate touching it. My motor reverses direction. I'm going to turn DI02 on to simulate coming off the limit switch. And now I am referenced, so I can turn this bit off and change to absolute positioning mode. So we're ready to position. We're going to go to 22.1 inches, so I'll type in 2210 because remember we have 2 decimal places, so that's my position. Now I better pick a speed. I want a nice slow speed, so we're going to run at 1 inch per second. That way it'll be really easy to count the rotations. And I'm going to pick acceleration and deceleration values of 100 inches per second squared. All right, we're ready to go. I'm going to turn this bit on and we're going to go ahead and count the rotations and see if we get in fact 8.5. Here we go. 1, 2, 3, 4, 5, 6, 7, 8.5. There we go, 8.5. So that clearly worked. That's our custom drivetrain with a custom user unit. And you can see everything works great. If this had been hooked up to a real application like conveyor or something with those pieces of equipment, we would have gotten 22.1 inches of motion. And that wraps things up. So let's just go ahead and shut things down nice and neatly. Inhibit things, release control, save our project. And that is the end of our final lab. Good work. And that is not only the end of session 16, that is the end of the class. I think you deserve a few gold stars. Thank you for taking this class. I hope you enjoyed it. I hope you found it interesting and useful. And I encourage you, come back to SEW Eurodrive USA. We have lots more classes here and we'll be adding more in the future. So I hope to see you in additional classes. Have a great day.